Let's continue working through some example problems to put into practice everything we've learned so far in this unit of study. So here's another problem off the AP Level C exam from the year 1989, and it involves a charged insulating sphere with a uniform charge distribution. Let's highlight that. Right, we're told that charges uniformly distribute out throughout the spherical volume. So we've got a few things to figure out. Once again, if you'd like to print out your own copy of this and read it before you proceed, feel free to hit pause now, print out a copy, and resume when you're ready. Okay, so let's carry on and take this all one step at a time. The first problem is to find the electric field that points outside the sphere. Okay, well, I suppose we should make a Gaussian surface, express Gauss's law, and recognize that the electric field lines are just as strong in this region as they are this region, so the electric field can be treated as a constant. Oh, and if this represents electric field, that represents an element of area, and the angle between them is 0 degrees. So you know the drill. The whole left side becomes E times 4 pi r squared. And then how much charge is inside? Well, all of the charge of the sphere lies within that Gaussian surface, so we can replace Q in with the full value of Q. And so, we just get that at points outside, in other words, for r, lowercase r greater than capital R, E is just equal to 1 over 4 pi epsilon naught Q over r squared, which is the same thing as KQ over r squared. So I could go the long way and explain how we can apply the expression v2 minus v1 equals negative the integral, a path from 1 to 2 of E dot ds. However, I think you know the result. For values of r greater than the radius, v is just going to be equal to 1 over 4 pi epsilon naught q over r, or in other words, kq over r. So the real challenge here is to find the electric field inside. And this might also be review, but it doesn't hurt to go through it. There's our Gaussian surface, so this time r is less, right? Now the whole left side of the equation that expresses Gauss's law still comes out the same way. So if we do a few steps in one, the left side becomes E times 4 pi lowercase r squared. Now Q in is no longer the full value Q. Okay, so what is it? Well, because it's a uniform charge distribution, we can go about this one of two ways. We could make this the integral of rho dv, and because it's uniform, pull rho out of the integral sign and replace dv with 4 pi r squared dr. Or, well, let's go ahead and do that and see what we get. So step 3 would be E times 4 pi r squared is equal to rho 4 pi integral of r squared dr all over epsilon naught, right? Rho 4 pi, rho 4 pi, and we're left with r squared dr. And we're integrating only up to the edge of our Gaussian surface. So from 0, not to capital R, that would, if we were to do those limits, we would account for all of the charge of the whole sphere. We're only trying to find, remember, the amount of charge inside the Gaussian surface. So from 0 to lowercase r. And that way the 4 pi cancels out, and we have E is equal to 1 over r squared. Let's pull this r squared to the other side. And then the solution to this integral is 1/3. Oh, and let's not forget our epsilon naught. So we'll say 1 over 3 epsilon naught r cubed. And so the r squared and 2 powers of r cancel here. And we get E inside is equal to, oh, and I left out this rho, forgive me. Don't forget rho. So is equal to rho r over 3 epsilon naught. Yeah, good enough. We can leave it like that, or we could substitute for rho capital Q divided by 4/3 pi capital R cubed. After all, rho is the full charge divided by the full volume. Okay. Let's see. Determine each of the following in terms of the quantities given. Well, then I guess we do need to make that substitution because we weren't given rho anywhere in the setup of this problem. Instead, we were given Q and R. So let's go ahead and answer in the language that the problem asks for. So step 6, En is equal to QR over 4 pi epsilon naught R cubed when everything cancels out, right? This 3 is going to cancel with that 3. And so we're left with 4 pi R cubed in the denominator along with epsilon naught. And we've substituted out for rho that way. Okay. And I'd like to point out, as I've done before, that if we make a graph of electric field versus distance from the center, then from the center up to the surface, this is a case where the electric field grows linearly. It's proportional to r to the first, and then beyond the surface goes as 1 over r squared. Now we need to come up with an expression for the electric potential inside. Okay, so here we do need to use the expression V2 minus V1 is equal to negative the integral from 1 to 2 of E dot ds. So we just say we want to find the electric potential just at some random point that's a distance r from the center. So we know here at the surface the electric potential is K capital Q over capital R. So let's let that be point number 1, and then we'll let the point we're trying to solve for be point number 2. So V minus KQ over R equals negative the integral. Okay, so point 1 is at R and point 2 is at lowercase r. And then this E is an E inside, so it's QR over 4 pi epsilon naught capital R cubed dr. So V is equal to KQ over R. Let's add this to both sides of the equation. Plus the integral. Let's make this a plus instead of a negative by flipping the limits of integration. Okay. So V equals, we see that 1 over 4 pi epsilon naught is the same thing as K. So I have that in both terms. So we'll factor that out. In fact, we can also factor out the Q. So we'll say it's K. Well, we can even factor out one of these R's, right? And change this to an R squared. So we can say it's KQ over R times the quantity 1 plus the integral from lowercase r to capital R of R, lowercase r dr over R squared. Saying a lot of R. I feel like a pirate. All right. So V is equal to KQ over capital R times the quantity 1 plus, I guess I could have taken this out of the integral, call that 1 over R squared, and then the integral of r dr is 1/2 r squared, so plus 1 over r squared times 1/2 r squared evaluated from lowercase r to capital R. right, there we have it. Now let's double check something. I guess no. Let's make this look a little better. Let's distribute this r squared. How about that? So v equals kq over capital R times 1 plus 1/2 the quantity 1 minus lowercase r over capital R quantity squared. A lot of brackets here. So when we're at r equals 0 at the very center, then this whole term goes to 0. And then we just have 1 plus 1/2. So we would have v at the center is equal to 3/2 kq over r. And I think you've seen that before in one of my previous video lessons. So that's nice to see that it agrees with a derivation we've already done before. Oh, and if r equals capital R, if we're at the surface, then this term, instead of going to 0, goes to 1, and then 1 minus 1, then that whole part goes to 0, and so we just get v equals kq over r. So v surface is kq over r. So it seems to agree with our expectation. So let's write that out one last time. V equals kq over r times 1 plus 1/2 1 minus lowercase r over capital R squared.